Hello friends, in previous session I have talked about the convergence sequence, Cauchy sequence in metric space, and also we defined complete metric space. A metric space XD is said to be complete if every Cauchy sequence in X is convergent. So we'll take few examples of complete metric spaces. While discussing Cauchy sequence, convergence sequence, I explained that open interval 0, 1 with respect to usual metric is not complete because there exists a sequence 1 upon n equal to 2 to infinity such that it is Cauchy sequence but it is not convergent because its limit is 0 and which is not in open interval 0, 1. That's why it is not convergent in that its limit lies in R1, Ru. Okay. So, firstly, we'll show that Ru is complete metric space. Ru is complete metric space. Okay. Solution. So on Ru, d of xy is equal to mod of x minus y for any xy belongs to R. Now take xn to be any sequence, Cauchy sequence in R. So let xn n equal to 1 to infinity be Cauchy sequence in Ru. We know that every Cauchy sequence in Ru is bounded. Since Cauchy sequence in Ru is bounded, therefore xn is bounded sequence. And every bounded sequence has convergence subsequence. Moreover, any bounded sequence in Ru has convergence subsequence. So let x and k equal to 1 to infinity be convergent subsequence of xn such that limit of xnk is equal to say x belongs to R. Now d of x and x is same as this is less equal to d of x and xnk plus d of xnkx. What I am doing, I am relating nth term of given sequence with this limit where the nth term of subsequence, kth term of subsequence by triangle inequality. Right. This is equivalent to mod of xn minus x is this equal mod of xn minus xnk plus mod of xnk minus x. Right. Now since xn is Cauchy sequence, therefore for given epsilon greater than 0, there exists positive integer n0 or n1 such that mod of xn minus xn is less than epsilon by 2 For any n greater equal n1. From 1, again from 1, for given epsilon greater than 0, for epsilon greater than 0, this fixed epsilon greater than 0, there exists positive integer n2 such that mod of xnk minus x is less than epsilon by 2 for any n greater equal or nk greater equal n2. Okay. Then for n greater equal n0 is equal to maximum of n1 n2 mod of xn minus x must be less than epsilon by 2 plus epsilon by 2 is equal to epsilon for any n nk greater equal n0 from 3 and 4 and therefore xn converges to x. xn converges to x. Right. And therefore every Cauchy sequence in Ru is convergent. And therefore Ru is complete metric space. Now if you take any discrete metric space, so let XD discrete metric space, we'll take a discrete metric space. I can take a metric space in which every set is open as well as closed. But here we'll take d of xy is 0 if x equal to y and it is 1. Okay. So let next example, let XD be discrete metric space with metric D defined as d of xy is equal to 0 if x is equal to y and it is 1 if x not equal to y. Okay. So that XD is complete metric space. Okay, that is discrete metric space is complete. Metric space is complete. Okay. So we'll take any Cauchy sequence. So let xn n equal to 1 to infinity, the Cauchy sequence in XD. Therefore, for epsilon is equal to half. For any epsilon, there exists a positive integer. There exists positive integer m0 so that d of xn xm is less than half for any m greater equal n0. In particular, d of xn xn0 is also less than half for n greater equal n0. Right? Therefore, but distance is either 0 or 1 and therefore d of xn xn0, therefore d of xn xn naught must be 0 for every n greater equal n naught, and therefore xn is equal to xn naught for every n greater equal n naught. Okay, and therefore limit n tends to infinity of xn is xn naught. Xn naught. Okay. Thus every Cauchy sequence in discrete metric space is eventually constant and hence convergent. What is meant by eventually constant sequence? A sequence xn is said to be eventually constant if all terms of that sequence except few terms are constant. Okay. So if all xn are constant except for few terms, or if all terms are equal, same, then we say that that sequence is constant. A sequence whose all terms are same, then that sequence is called as constant sequence. And constant sequence must be convergent, because as n tending to infinity, every term of that sequence is same. Distance between any two terms xn and that fixed x must be 0 less than epsilon. Even from first term n naught is equal to 1 exists for that constant, and for eventually constant sequence also. A sequence xn is said to be eventually constant if xn is equal to x for every n greater equal to n naught for some n naught. So for eventually constant sequence, xn becomes xn naught after n greater equal to n naught, and therefore that sequence must approach towards that fixed number. Is it clear? So thus we proved that every Cauchy sequence in discrete metric space is eventually constant and hence convergent. Therefore, discrete metric space is complete metric space. Discrete metric space is complete. Right? So we have proved that set of real number with respect to usual matrix is complete. Set of real numbers with respect to discrete matrix is also complete. Okay, is also complete. Now we'll take the example. Rn is complete metric space. Example, Rn with the D2 or any D1, D2 or D infinity is complete metric space for fixed n greater equal to 2. Solution. Let Pk k equal to 1 to infinity. Pk is equal to say x1k, x2k and so on xnk. The Cauchy sequence in Rn. Okay, in Rn. N greater equal to is fixed. Therefore, for given epsilon greater than 0, for given epsilon greater than 0, there exists some positive integer n naught such that d2 of pkpl is less than epsilon for any kl greater equal n naught. By definition of d2, this is nothing but summation of xik minus xil raised to 2 I equal to 1 to n whole thing raised to half. This must be less than epsilon for any kl greater equal n naught. If I take the square, therefore summation of xik minus xi raised to l its square I equal to 1 to n. This must be less than epsilon square for any kl greater equal n naught. Therefore, xik minus xil square, this is also less than epsilon square for every I equal to 1 to up to m. Okay. Since a square is greater equal to 0 for every a belongs to R. So this is the sum of squares, sum of non-negative terms, and their sum is less than some number, means every term in that sum of non-negative terms must be less than that right hand side. If positive negative numbers are contributed, then some term may be greater than that. But the squares are greater equal to 0, and that's why we are getting this. And therefore, mod of xik minus xil is less than epsilon for any kl greater equal n naught I equal to 1 to up to n. What this implies is xik k equal to 1 to infinity is Cauchy sequence in Ru is omitted for every r. Now we proved that Ru is complete metric space. Since Ru is complete metric space, therefore each Cauchy sequence xik is convergent in Ru. Suppose limit of xik k equal to k tends to infinity is equal to xi for every I equal to 1 to up to n. Playing limit k tends to infinity of pk must be p is equal to x1 x2 up to xn belongs to Rn. This xi lies in R and therefore p lies in Rn. Is it clear? Now from this say 1, from 1 for given epsilon greater than 0, there exists Ni belongs to n such that Ni belongs to n such that mod of xik minus xi is less than epsilon upon root n for every k greater equal ni. For every k greater equal ni. Right. Choose n naught is equal to maximum of n1, n2 and so on, n. Then mod of xik minus xi is less than epsilon by root n. Okay, for every k greater equal n naught. Okay, I equal to 1 to up to n. And therefore, summation of I equal to 1 to n xik minus xi square is less than n times epsilon square upon n. For every k greater equal n naught. For every k greater equal n naught. And therefore, summation of, if I take the square root, I equal to 1 to n xik minus xi square raised to half. This is less than epsilon for every k greater equal n naught. And therefore, d2 of pk, p is less than epsilon for every k greater equal n naught. Sorry, here n is taken to be capital. Right. This implies is limit k tends to infinity of pk is equal to p. Thus, every Cauchy sequence in Rn is convergent. Thus, every Cauchy sequence in Rn d2 is convergent. And therefore, Rn d2 is complete metric space. We know that three matrices for Rn, d1, d2, d infinity are equivalent matrix. So, equivalent matrix preserves convergent sequences, Cauchy sequences. Therefore, whenever the given Cauchy sequence is convergent in Rn with respect to d2, it must be convergent with respect to d1. It must be convergent with respect to d infinity metric also. So, with respect to any metric among d2, d1 or d infinity, Rn is complete metric space. But with respect to discrete metric also, Rn is complete. Rn is complete metric space. Is it clear? On same line, you can prove that LP is also complete metric space. Okay. So, we have taken LPDP. That is exercise 1. Okay. Exercise show that LP DP for 1 less equal p less than infinity is complete metric space. Is complete metric space. Okay. So this is exercise for you. Okay. Try to prove this to be a complete metric space. So with this discussion today, we'll stop our session here. Thanks for listening lecture session carefully. Bye bye.